So here I am presenting my CML assignment. Here I am going to show the part C assignment. Before we begin the assignment, let's go back to the doc share that our professor had shared with us so we can better know about task that we have to do. So here the part C of the video that we have to make. So we have to basically make a video explanatory video which duration about 10 to 15 minutes. So we have to make a presentation on the generation of X-rays, and for the reference we have to use the text of the Girolami where generation of X-rays has been given on the chapter 13. So basically we have to go through the chapter and to study about it and to make a presentation. So that's what I have done here. So let me just go over my slides and to show let me show you. So here is my slide. Let's go to slideshow, play from the start. So here my assignment, cml-102 assignment 1 part C. It is presented by me. My name is Tushar. So let's begin with the presentation. So if you look at the man, he is William Roentgen. What does he do? Let's find out. So basically in the slide we are going to saw discovery and the basics of the X-rays. So discovery happened in 1895 when William Roentgen was discovered X-rays in 1895 while he was studying the cathode rays. Basically he was not aiming to find X-rays. He was basically keeping his study of X-ray cathode rays. So in those time when he was studying about the cathode rays, he observed mysterious glow through a barriers when electrons struck certain materials, which led him to identify new form of radiation. It was unknown at that time. The ray that the radiation that he has observed was unknown at that time. He observed some peculiar characteristic about this radiation, which is as follows: the wavelength and the energy of the radiation. He observed that the wavelength is extremely short, up to order of 1 angstrom, that is 10 to the power minus 10 meter, which gives them very high energy. Like this radiation that he has observed are very high penetrating radiation. So since there no name was there, he decided to name it as a X-ray because his the properties of this radiation was unknown at that time. So that's why he named is X-rays. So these are the few properties of the X-rays, that they have very high energy and high penetrating power. They have very short wavelength. So let's go ahead. So now we will study about generation of X-rays in the laboratory. We can generate X-rays in the laboratory itself too. So how can this be possible? Let's study that. So let me start with this figure here. As you all can see here, this is a diagram of an X-ray tube. So the X-rays which are generated by electrons from the cathode filament striking the anode exit tube to the beryllium window. So what is happening here? Here you can observe a cathode. So basically cathode is generating electron here, which is like high energy electrons are generated from cathode, and it hit the targeted material anode. So when it hit the anode, so basically what happens here, as we will see further in this slide itself, that the electrons are ejected from the anode, and then some process happen, and which leads to the radiations coming from the target material, which is known as the X-rays. So when the X-rays are here, it's absorbed by the beryllium windows here. So because beryllium being a good absorber of the X-rays, so it absorbs the X-rays here. We have coolant here too, like because the X-rays are very high energy, so due to the very high energy it can heat up. So we need coolant here, like water help in cooling the system here, so that its temperature can be remain constant. So let's come here for the preparation and how it works. So X-ray tube structure. Sorry. X-ray generation relies on high voltage setup where electrons are accelerated and directed at targeted material. The setup includes a cathode, which is act as an electron source here, and an anode, which is a target source here. So basically what happens here, we can see in the functioning part: upon the impact with anode, electrons releases energy in the form of X-rays. So what happens when we just bombard electrons from the cathode to the anode, the targeted material, it on impact it causes the electrons to get knocked out, which then releases energies in the form of the X-rays. Higher the voltage you applied, higher energies access you will get. So this is the basic principle of generation of the X-rays in the laboratory. Let us move ahead. So now, as we know the basic properties how the X-rays are generated, so now we can dive more deeper into it. So we can read about the type of X-ray radiation. So there are two types of X-ray radiation. First being the white X-ray radiation, and the other being the characteristic radiation. So we will start with the white X-ray radiation. So white X-ray radiation, also known as Bremsstrahlung radiation. So what happens in this? It is generated when electron deaccelerate upon hitting the target, producing a continuous spectrum of X-ray wavelengths. So in this, what happens that when from the cathode you just bombard on the anode, so the electrons on striking, it just deaccelerate itself. On deaccelerating, it releases energy. The energy releases here is in continuous form, and this continuous spectrum of the X-rays is known as the white X-rays. Why it's known as white? Because since the white light has multiple wavelengths in it and it's a spectrum, so that's why it's known as like a white radiation. So here the minimum wavelength lambda that can be calculated, we can calculate with the help of the given formula. Lambda minimum is equal to hc over Emax. Emax is the maximum energy that is possible. So as we all know that maximum energy can be written in terms of charge and potential. So here we write Emax as hc by over Eu, where U here is accelerating voltage between the anode and the cathode. Cathode is the source, anode is the targeted material. So here we can see that if there is incident electrons and this is the target material anode, so there's some electrons or some nucleus or some atoms will be there. So on coming to the interaction, electrons got deaccelerated here, and which caused lead of the X-rays. These X-rays that just radiated here are known as the white radiation. Let's move to the next form of the X-ray radiation. So the other type of X-ray radiation is the characteristic radiation. The peculiar thing about this radiation, it is that it occurs when high energy electrons knock out the inner shell electrons in the target atom. So when you are bombarding from the cathode to the anode, the electrons are really high energy. So when they went to the anode, they just knock out the inner shell electrons of the anode shell, like a targeted atom. When they knock out them, it creates a vacancy. Then outer shells of the electrons of the anode comes to fill this space. When they come here, they emit some accelerated radiation, and this emission radiations are labeled as K, L, M, and etc. What are these K, L, M, and alpha, beta, gamma? We will just learn over this on the next slide. Okay. So one of the more important thing is here, the resulting X-rays give sharp peaks in the spectrum and are called characteristic radiation. So we obtain a really high energy peaks here. So like in case of white radiation, it was not it was a continuous spectrum, but in case of characteristic radiation, it is sharp peaks. We will observe it in the next slide. Okay. So the other thing is about energy. So the energy of each characteristic X-rays is approximately equal to the energy difference between the two orbitals. Here we talking about the orbitals from which you are knocking out the electrons, and the other orbital from which the electron is coming to fill that space. So the energy difference between those two orbitals is defined as delta E. So the characteristic wavelength lambda is defined as hc over delta E. So let's move ahead. So let's dive more deeper into the characteristic radiations. Sorry. So this is a notation here. X-rays from electron transition to a specific shell are labeled as KL, etc. And other things are alpha, beta. What are these? So the transition within the same shell but different energy levels, like the shell remains same here but the energy levels are different here, are denoted as alpha and the beta. So let's begin with the K radiation. What is K radiation? When an electron fills alpha vacancy in the 1s orbital, it emits K radiation. Like when an electron fills a vacancy in the 1s orbital, so it is a nucleus here, 1s orbital is here, and oh sorry for this sound, someone is bombing outside. So when from the first cell it comes to the 1s cell, like when it fills the 1s cell. When it comes to the next cell, it is known as k alpha. When it is coming from the next to next cell, it is known as k beta. Similarly, if it comes from next to next cell, it is known as k gamma. So that's how we name it. So if it is coming in the 1s, it's named as a k shell. If it is coming to the L shell, so it is known as L alpha, like 2s cell or 2p cell. If it is coming, so it can be known as the L cell. So it depends on if it coming just from the next orbital, it's an L alpha. If it is coming from next to next, then L beta. Similarly for L gamma and other things. So I hope this is clear. So, and one of the important thing here, in the L radiation emitted from transition to 2s to 2p, that is known as L shell. We just discuss it. But important thing is that L radiation has a very lower yield in the X-ray tubes and is less commonly used in X-ray diffraction. So we basically study more about the K alpha, K beta term, not about the L alpha because of their low intensity. Let's go ahead. So here is the X-ray intensity versus wavelength we are showing here. So these are the two types of radiation that we have discussed. Here being the white radiation, here being the characteristic radiation. So you can observe here that the characteristic radiation have sharp peaks here, and the white radiation have a continuous spectrum. You can see here. So basically, it is the X-ray radiation from the hot cathode tube as a function of accelerating voltage applied. The more the voltage you applied, more will be the intensity. As you can see, the 5 voltage have low intensity, 15 voltage, and then 20 voltage and 24 kilovolt, it has a high intensity. And you can also observe that characteristic radiation has a real high intensity in comparison with the white radiation. That's all about the type of the X-ray radiation. Now we move to the practical use. Sorry for this bombing, I don't know who are bombing here. So let's begin with the filtering of X-rays. So what do we mean by filtering of the X-rays? So basically, X-rays can combine of the different wavelengths. It's not like that, it's just a comparison of single wavelength. So it can have multiple wavelengths there. But for the practical uses, like we need it to be a monochromatic. Being a monochromatic will make it like a very highly peculiar characteristic with high energy, and it can be used in different aspects. So let's begin how this can be achieved. So before talking about filtration, let's go over to the some basic concepts. So this K alpha and K beta that we discussed earlier, they act as some like mono, not they are basically the K alpha 1 and K alpha 2. This K alpha 1, K alpha 2, you can see here what were they. K alpha, that is K alpha. So basically, the like just next to it, so K alpha 1, K alpha 2, K alpha 3, we can name it like that. So they are have a nearly identical wavelength because they just differ by 1%. So they almost behave as a monochromatic. But if we went to the K alpha and the K beta lines, here we can see K alpha and the K beta. So now they are distinguished, and their line differs about 10% in wavelength. So this disturb the monochromatic behavior and act as like it has multiple wavelengths. So, but one of the important thing is that here K beta is like lower energy. As you can observe here, K alpha is a strong radiation. K alpha is a strong radiation here, and K beta has small energy. So here we can discuss more about it. So basically, K beta is typically filtered out to enhance the stronger Ka radiation. How we are going to filter it out? Let's discuss more about it. So let's about before discussing that, we discuss about the absorption and the penetration. So look, if you have a shorter wavelength, it implies a higher energy. So X-ray penetrate materials more easy. The shorter the wavelength, the energy higher the energy. If the energy is very high, then absorption would be very low, very low. But at certain point, with X-ray energy is a specific reaches a specific threshold, it can eject electrons from the K shell. Like it just knock out the electrons. When it just knock out the electrons, it causes certain increase in the absorption. Like when it just knock out the electron, then electron could absorb the material, and there is a sudden rise in the absorption, and it's known as the absorption age or the resonance age. So I can show it with the help of the graph. Let me show it. So like it is shown here. So as it is wavelength represent absorption, as we decreasing the wavelength, the energy here is increasing, so there is a less of absorption taking place. And at a certain threshold, there is certain peak occur. like there is an sudden increase here that has been observed, and this is called K absorption age that is take place here. And then after this point the behavior is very similar, that wavelength is decreasing and that's why energy increasing and absorption is decreasing. So this portion is known as the absorption age, and that's a very important point that will help us in filtering. And how will it help, we will see. So use of the absorption filters. X-ray filters are often used to remove unwanted wavelengths. We as we know we wanted monochromatic wavelength, so we don't want multiple wavelengths to be there. So we try it to be a monochromatic one. So basically we try to remove the K beta, because K beta is like a weak weak signal here, and K alpha radiation is the strong here. So we nearly, if you want to produce a monochromatic alpha beam, we need to use some filters. Then how will it work? Let's see. So here X-ray absorption filters are there. So it can be done with the help of the nickel compound. For the copper, nickel compound helps. How, for the other compound, what should we have to do? We will see. So absorption age filtering with the nickel. So the abrupt increase in the absorption at the X-ray absorption age allows for the selective filtering. Here we are talking about this abrupt increase. For example, nickel, the atomic number is 28, as an absorption age between the K alpha and K beta of the copper. Here you can see the copper is here. So let me just go back. So it's copper K beta here and copper K alpha is here. So basically thing is happening. Uh, so it lies here between the K alpha and K beta regime of the nickel nickel absorption age. So it can help us to filter one portion of it and to pass the other part of it. Okay. Selective absorption of K beta radiation. So what we are doing here, let's see. So we are just absorbing K beta radiation selectively. Nickel absorbs the K beta line from copper about 6 times more strongly than the K alpha line. So the absorption for K beta is more, so we can just absorb the K beta here and just filter it out, as simple as that. So we can get a cleaner K alpha beam. So that's the basic principle. Here you can see more about it. Copper X-ray emission spectrum. It contains both wide radiation and characteristic lines, like the it's the characteristic lines here, and it's the spectrum is of the wide radiation. Okay. So after the filtration is done, we just can see that nickel causes copper K alpha to pass only, not K beta. So we get this step. Let's move ahead with it. That's how the filtration works. Then synchrotron sources. So let's move to the last topic of our discussion. It's called synchrotron sources for X-ray generation. So what are the synchrotron sources, and why we need synchrotron sources at the first place, and what this image is here representing? So let's discuss. So we need high intensity X-rays. Why we need high intensity X-rays? So let's begin. Why there is really need of it? For very small crystals like less than 0.05 mm on the edge, traditional hot cathode X-ray sources are insufficient, because they can't provide because they provide very weak diffraction pattern, and it doesn't contain much information, so we can't infer much from the X-ray diffraction method. So synchrotron sources are essential to generate high intensity X-rays. We really need high intensity X-rays to be get generated. So what we do here, let's see what are the synchrotron sources. Basically, synchrotron consists of the evacuated pipe curves in the large ring, often tens to thousands of meters in diameter. Electrons are injected into these pipes and accelerated to high speeds. Basically, these are, here you can see these are long pipes are connected here, and we are just, what we do, we just put some electrons there, and with the help of the magnetic field which help them to move the directions here, and then with the help of the electric field we accelerate them. Upon accelerating, we can make them to reach the speed of light here, and with such speed the magnets are used here to bend the electron path. Electron change the direction and speed close to the speed of light. They emit intense X-ray radiation. So we can get the high energy X-ray radiation from the synchrotron sources. From the synchrotron sources. Okay, so advantages of the synchrotron radiation. What are the advantages? Let's discuss. So synchrotron radiation is up to a billion times more intense than the normal X-ray radiation. So like it's billion times more strong. So due to this intensity, X-ray diffractometer are installed at most synchrotron facilities for advanced structural studies. So whenever you need like high diffraction, you need to study the diffraction part, and you want high energy, high intensity X-rays, you can use the synchrotron sources. So that was the last topic. So we can conclude what we have studied so far. So we have studied about how the X-rays are generated, how things happen. Then we just see how we can generate a monochromatic X-rays and how the filtering process has been done there. Then we just hover to the synchrotron advancement. That's how we can produce high intensity X-rays beams, and that's all that we have discussed here. We can also come to the application part here, X-ray being the futuristic thing. The advancement in the X-ray technology, form filtered X-ray tube, high intensity synchrotrons, continue to expand application in the field like material science. We can know more about the materials, defects, properties, and many things. Biology, here we all know that X-rays are widely used in the aspect of biology, and chemistry too. It helps us to reveal the structure details critical to the scientific progress. So that's all about the X-ray generation. Let me just go on the first page here. So that's all from my side. It's my part C of the CML assignment presented by Tushar. Thank you for hearing me out. Hope you have a nice